Okay, gentlemen, we were talking about work and energy, and we would extend that discussion to few more points, and then we can see how we can apply that definition to find out work in a thermodynamic process. Okay, so generally those thermodynamic systems include one of a very generic description of those kind of systems. I mean, that is gas in a cylinder, right? So I would explain that phenomena, and then we would see how we can find out work in that particular process. So I am going to talk about expansion or compression work. And the system which we are going to talk about, that is gas in a cylinder. To derive that, just look at this system. We have a piston cylinder arrangement. I would say that this is kind of so what you can see is this is a piston, and here you can see some gas or liquid, some kind of fluid. So obviously this gas would exert some kind of pressure on this piston. Okay, so if it is doing this thing, that means applying pressure on that piston, it means there would be a force felt by this piston which is being applied by this gas, right? And you already know that this P would be somehow related to this force, and that force is there. If you divide it by area, you would come up with that pressure. Okay, it's a simple thing. So due to that pressure, for example, this is one equilibrium state. I hope you understand what do I mean by equilibrium state. This is first equilibrium state. Some kind of balance is there. Okay, the system is not going to move. Some kind of balance is there. You do something with the gas. Let's say you heat it, or somehow or the other you provide some energy to this gas, and as a result of this, it starts expanding. So once it starts expanding, it would try to exert some pressure on the piston, and obviously the piston would start moving. Okay, so if this piston starts moving and it has gone to a new point, which is basically x2, and I would say that this is another equilibrium position. So in that case, we are going to see how much work has been done by the gas on the piston. Okay, so that's the question. So that force was equal to PA. P is pressure, and A is the area on which that pressure is exerted. Okay, so I mean, if you want to find out work, what is a generic definition? You simply multiply force by displacement. And if you look at, you can say the real definition, that work could be described by this thing. Once it has gone from S1 to S2. Okay, And just to make it mathematically consistent, I told you something about inexact integral and exact integral. So what you can see is, to make it mathematically correct, okay, before that let's do something. I say that there is a small amount of work done by the system once it moves the piston from position x1 to position x2. That would be something like f dx. Okay, dx is the small amount of displacement which the piston has covered, and then this f would be equal to what? Pa dx, right? This is pressure multiplied by area, and you know that what would be this thing? Isn't it kind of a volume, right? So you can say that this would be equal to P dV. So finally I come up with this expression, delta W equals P dV. And now to make it now this is a you can say demonstration. Why do we use this delta W sign? Because if I need to find out the total work involved in this process, I need to integrate on both sides. Okay, if I just have W over there, so I won't be able to integrate it, right? So this is mathematical consistency. So I need to have that delta W sign, which is basically an inexact integral. That's the user which knows about this thing. Okay, so you should know that this is an inexact integral. Inexact integral. By the way, this work is not a property. It means you can't define work at x1 or x2. You have to define work which has occurred from x1 to x2, right? So from between two states, it is not a property. So similarly, but this one is the exact integral. This is basically a property, is exact integral, I would say. So finally, you would come up with this expression that W would be equal to P dV. Okay, it means how you can find out work in those kind of expressions. Because of this integral sign. And obviously if you have to put limits, it has to go from V1 to V2. I mean, this is the volume sign, V1 to V2. So whenever some work is involved due to the compression or expansion of a gas, so whenever there is some kind of work involved like this, how you can find it out? Work is equal to pressure integrated over the volume swept by the piston during that process. Okay, so this is very important to understand. Now the question is how you can find out pressure as a function of volume. I mean, this if you look at from applied point of view, obviously this pressure can only be integrated by volume. Let's say if you have somehow or the other pressure becomes a function of volume, isn't it? So how we can do that? We can say that I have a piston cylinder arrangement. Now please be very careful and try to understand this concept, because again there are few concepts which look very easy, but they are not like that. Okay, you have to understand what is the fundamental thing behind them. Now you have a piston cylinder arrangement, and what you do is that you have installed a pressure sensor on the piston just to measure how much pressure is being exerted on that piston by the gas. Okay, so you have installed some kind of pressure over there, and somehow or the other you also measure the displacement covered by the piston. So you know the cross sectional area, you can cover the measure the displacement covered by the piston. So what you can see is that you can plot this thing, that for example at pressure P1 you have this pressure V1. Okay, and after that, after some time, it is basically moving, and then after 1 second or let's say few more seconds, you find out that once pressure comes up with this value, you have this V2. Okay, and finally what happens is that as you increase the volume, pressure should be decreasing, right? Pressure should be decreasing. So it means it is going like this. So once you join those 2 points, you have this kind of curve. Okay, this kind of curve is known as PV diagram, right? So this is very, you would occasionally see these PV diagrams. They are often used in thermodynamic analysis. So let me show you one more point about this very important concept. Yes, look at this figure. So there are 2 kinds of data. You can say those circles with a dot inside, this is a measured data. I mean, that data has been obtained from the sensors which you have installed on the cylinder and the piston, right? So if you have got those data points, then what you try to do, you can see that there is a certain kind of scatter. Those data points, they are not coming on the straight line. Okay, so there is a certain scatter, and what you can see is that finally there is a curve which is approximating that data. Okay, which is approximating that data. Now that curve used to fit that data. There is a technique known as curve fitting. There is a technique known as curve fitting. I am not going into the basics of that technique, but you would see its application in your course on numerical analysis. I don't know in what semester you are going to take that course, but still this is the course which would deal with that curve fitting. Somehow or the other, there are mathematical techniques by which you can find that out. But my point is that there is some curve which is going to approximate that data. Obviously by those unknown techniques, you have not still any idea about that, but there is some curve, and I need to know what is the equation of this curve. Obviously those techniques on curve fitting, they would give me the equation of this curve. Okay, this is something known as data fitting or curve fitting, right? Now my point is, I can use this equation of the curve to find out the dependence of pressure on volume, or let's say the dependence of volume on pressure, interdependence. I can't say this is the independent variable and this is the dependent variable. I can't distinguish that. So what I can see is somehow or the other I come up with that curve. So if I ask you, if you want to find out work from that curve, how would you be able to do that? You should find out area under the so that's how you integrate it. Okay, I mean that is something which is always confusing. I mean, up to your first semester, okay, fine, then you could have said that, okay, but yes, exactly, you can say that. I mean this, but because I am drawing it on over there, and this is basically pressure dV, so I am integrating pressure over volume, right? So that's why I am using it. So anyways, let's see that this is the area under the curve, and this area would tell me how much work has been done by the gas on the system. Okay, by the gas on the piston. So it means, would that work be positive or negative? If the system is doing work, it should be positive. Okay, so this is quite important to understand. Then let me show you one more thing. Yes, before going further into this topic, let me explain one concept. The point is, if some process is occurring, now again, be very careful, and try to understand the terminology. Okay, if some process is occurring, you may be in a state where you can't say that the system is in equilibrium. Okay, for example, if this is first state of the piston and this is the second stage, the piston starts moving from this point to this point. Okay, and then you can see that this is the first state which is in equilibrium and this is the second state which is in equilibrium. If the piston starts moving, you can't say that during this process the piston is in equilibrium. Okay, somehow or the other it is trying to achieve second equilibrium stage from the first one. Okay, let me explain it once more. This is state 1. This is where equilibrium was for piston and that cylinder assembly. There is a gas. Somehow or the other you have achieved some kind of balance between the forces over there, and it is there. The piston is not moving. Somehow or the other you heat the gas or you do something with the gas and it starts expanding and the piston comes to a new state within this one. So you can see that the piston has not straight away come from this point to this point. What it has done is it has slightly moved and then it has been covering some distance, and after some time it has reached that state and then it has gone into an equilibrium state. Right? That balance would again be there. So my point is, but still you see that this is state x1, this is state x2. Okay, so what you can see is that some work is being done on the system, that's why it is moving, right? And during this process you are trying to measure volume and pressure. During this process you measure pressure on this point, you measure pressure and volume on this point, similarly this point, similarly this point, but all the intermediate states, they are not equilibrium states. Do you understand my point? All the equilibrium states are not equilibrium states. Even in the case of what? Yes, this is not in the equilibrium state. Okay, I'm not talking about from mechanical point of view. Just see, this is the thermodynamic principle. So balance means somehow or the other this stops over there. Okay, so my point is that even though it is not in equilibrium state, but we are measuring its property. Now for example, if at this point I say that pressure is this much, volume is this much, but at the very next instant the piston would go to the other state and then your pressure would change, right? So it would be very difficult to find out work. It would be very difficult to find out work based upon those non-equilibrium states between x1 and x2. Okay, so my point is, how do you see it from an engineering perspective? Okay, you would see this term, the heading of this slide, you would see this term again and again, and it is very important for you to understand it. Now these kind of systems are dealt with in engineering because you should be able to measure all the properties at equilibrium stages. What you can see is you consider all the intermediate states as if you were in quasi-equilibrium, almost equilibrium. Okay, this is a technical term. So although you are not in equilibrium, but you consider your system to be in quasi-equilibrium, almost in equilibrium. Now what do you mean by it? For example, just consider, don't look at this figure, let me give you one example. Now there is a bird which is flapping its wings, right? And I would say, now for example, you just consider an aeroplane wing, and all the aerodynamic theories, you can use those theories to find out its lift. Considering this whole wing on what? On a static position. I mean, it's not going to move. I'm talking about wing of a commercial airplane or something like that. But once you come onto the wing of a bee, or let's say, or insect or bird, it starts moving, right? Now see, can you apply the principle of aerodynamics which are true for that static wing on this moving wing? You can't do that. I mean, you can't do that. Now why? Because for example, if the wing is on this position and it has come to this position, obviously the lift produced by this wing on this position would be somehow or the other dependent on its lift on the previous position. I mean, those moving systems, they have some kind of history behind them. Okay, and that history is going to affect their performance on the next time instant. Okay, this is the difference between the moving system and a static system. So you can see that this is moving, so you can't see the theory of a static wing applied onto this moving wing. Why? Because this moving wing carries its history. Okay, and that the forces on this position would be affecting the forces on this position. Similarly, on this position, obviously both of those two previous positions would be affecting the new one. So this is my point. But in engineering, for example, either you go for the very complex analysis, which is very hard. By the way, this is a moving boundary. I mean, if you use that kind of moving boundary with the fluid mechanics equations, it becomes really hard to find out the solution. Okay, but what people do is they consider their wing first at this stage, apply that aerodynamic theory for the static wing when the wing is in this position. Then they jump into the other one. They say that, okay, fine, let's apply the theory on this next position. They go towards this point. They say that, okay, fine, we have a new position. So we can apply that static wing theory on this position, right, on this wing. So you can see that what are you doing? You are trying to decompose the whole video into small snapshots, right? By looking at one snapshot, can you find out what was the history behind that? You can't do that. So just consider that you have a series of snapshots with you, and in one stage you have a video. These are two different things. Video is something which is carrying its history. By looking at the video, you can find out what was the history of the system. But by just looking at the snapshots, you can't find out. Do you understand that? I mean, you can't say what happens within the time between two snapshots. You can't say that, what happens between that, right? So you can say that video is kind of a non-equilibrium process which is constantly moving. But what you have done is you have decomposed the whole non-equilibrium process into small equilibrium processes. You have a picture, it's kind of an equilibrium process, right? Similarly, just look at that wing. If this is in this state, you say that it is in equilibrium. But you know that it is not actually equilibrium. So what you can see is, for engineering analysis, you use the word quasi-equilibrium. You use the word quasi-equilibrium. So you use the term what? Quasi-equilibrium. It means that it is not an actual equilibrium. It is an almost equilibrium. Now how you can defend that? This is something which is an equilibrium state for a wing. So I give a very small jump to the next position, a very small jump, and I say that, okay, the jump was really small and it is not going to affect much of that equilibrium position, right? So I say that this is a quasi-equilibrium. So just look at that figure in the slide. There are so many small masses which are there on top of the piston, and what you can see is, if you want to increase its volume, now this is first equilibrium state which you can see over there. Now just pick one small mass out of this system. What would happen? A very small change in the volume would occur, right? So this is, you can say, this is, although this is basically undergoing a process, the system is undergoing a process, but what happens is that the shift from the equilibrium state is very small. So the next state, once you pick the mass, a small mass out of the system, the next state would be what? Not the equilibrium one, but which one? Quasi-equilibrium, right? Similarly, you start picking, so just like if the piston is going from this position to this position, you can just imagine that system as if you are picking few masses out of it, and every mass particle is very small, that it does not affect the equilibrium position to a large extent. Do you understand that? So this is how you define quasi-equilibrium process. So if you put any word like this, I mean, I was talking about the wing. So generally this theory which is applied on a static wing, this is known as a steady state aerodynamic theory. So for example, if I am trying to apply that steady state theory on this rotating wing, or let's say oscillating wing, I would say that I am trying to use it in its quasi steady form. Do you understand that? So quasi means almost. You are considering that as if your system is not moving from the original equilibrium state to a very large extent, it is a very small move, right? So yeah, obviously state will change. That's why you can say that the system is moving from one equilibrium position to the other one. Okay, but this is just for the mathematical analysis, and I mean most of the time you would deal this with this word, this term, quasi equilibrium or quasi steady kind of phenomena. You can say that, yes, you can say that. You are taking picture out of the whole video, and then you are taking another picture, then you are taking another picture, right? But the duration between those pictures, or you can say time gap between those snapshots, it's very small, as if you have not moved to a large extent. Okay, but obviously in reality you are doing that. So that's how you deal with mathematical concepts related to the actual processes, right? I hope there is no question about equilibrium or quasi-equilibrium.
In case of birds, they are constantly moving their wings. But in this case, when you remove a small length, then it is in actual equilibrium. Then why we are using the term quasi-equilibrium?
I mean, it's not that easy. I mean, you are just imagining that. You are just considering it. Actually, you don't put masses on that piston, right? That's how you perceive it. Do you understand? Just like the wing, although it is constantly moving, but you are perceiving as if it stops there, then it stops there, then it stops there. Can the bird actually flap its wings like that? Not at all. I mean, it's constantly moving, but for your engineering analysis, what you do is, otherwise you can't deal with it mathematically. Or I would use the word, you can't model this phenomena mathematically. Right? So just try to understand this word as well, mathematical modeling. I mean, what I'm trying to do is, I have introduced a new term, quasi-equilibrium, just to do what? Mathematical model. To develop a mathematical model for the system. Okay? So just see that P, dV and integral equals work, that is what? That is the mathematical model for this thermodynamic system. Sorry, can you repeat that? When a complete equilibrium, I mean once the system, once there is new balance state, there is a new equilibrium position. You can say that. Obviously, if some work is being done on the system, its volume would expand and it would move up to a new position. Okay.
That if suddenly all the masses are moved, then we can actually measure the volume of the system and the pressure of the system as they depend on the states of the system, but we cannot actually measure the work done on the system.
You can say that.
It depends on the process.
Yes, exactly. Why the process hasn't stopped yet? Okay, so it has to go to a new equilibrium position to define work. If the system is not in. No, not all the time. Not all the time. I mean, I'm telling you I'm explaining one terminology. How do you mathematically analyze those processes? I mean, the system is moving and still you are measuring its pressure and volume. How can you do it? Because once you measure it, you can say that the pressure sensor might be giving you value after some lag in time. Do you understand that? So this is not an equilibrium position. I mean, but still you are considering as if it is in quasi-equilibrium, just to mathematically model this. Okay. So new equilibrium position would be there at x2. I have already explained it. No, you are not calling x2 as the quasi-equilibrium. You are calling all the intermediate positions between x1 and x2 as the quasi-equilibrium position. So this is something which is known as work, and I mean, you should understand how that quasi-equilibrium process is defined. And let me tell you one more thing. I have already told you that work is not a property. I mean, these are few salient points. Work is not a property, and for example, if generally you look at this curve fitting, the curve which is fitting their data between pressure and volume, that curve is generally defined as PV raised to power n equals some constant. And these processes are known as polytropic processes. Okay, so this n and this constant, they are determined empirically. Now, what do you mean by empirically? That you perform some kind of experiment, you try to fit some kind of curve on that data points. And how do you do that? Using the techniques which would be taught to you inshallah in your numerical analysis course. So how do you do it? You do it by curve fitting, and you come up with that n value and that c value. Okay, for a certain system you can do that. So now the question is how we can apply that. How we can apply that mathematical model to find out actual work. So let me give you a simple example. For example, if you have some value of n and some value of constant, and you are asked to find out work which has been done on the system from, let's say if the system goes from, piston goes from state 1 to state 2, what you can do is PVN is equal to constant, and you know that work is equal to what? TdV. So obviously you have to represent this work as a function of volume, right? So if I see this equation, I can say that P would be equal to what? Some constant over V raised to power n, right? So I can say that this would be from V1 to V2 some constant over V raised to power n dV. Now can you integrate this system? It's very easy. I mean, there is a constant term and then you have V raised to power minus n. You know that V raised to power minus n plus 1 over what? Minus n plus 1, something like that, right? So you can integrate it, and then you need to put the limits from V1 to V2. Okay, so that's how you use this mathematical model to actually find out work for some process. Okay, let me give you some examples for some other processes related to work. First example is, another example is, you can say, not the first one. Extension of a solid bar. I mean, how do you do it? For example, if there is a bar just like this one, you apply some force, and as a result it covers some distance, and this is the new position. You know that all these bars can also be modeled like a spring, right? You apply some force, obviously there would be some kind of strain into it, right? And then you would say that this is the displacement which has been covered by as a result of this force, right? So once this force applies some pressure on it, this would be equal to F over A, and obviously how much work would be done on that? This would be pressure into what? Into dl, right? That's how you define it. And if I want to look at it from a more mathematically rigorous analysis, you can say this is PADL, and this is delta W, and then you integrate it. This is an inexact integral, and this is the exact integral, and finally you come up with something like work equals PADL. I mean, there is another notation instead of so this is PADL, and what you can see is that you apply pressure. Remember that there are few, you can say, confusions. You apply pressure, and as a result stress would be developed inside the material. Remember that, okay? You apply pressure, and then as a result stress would be developed in. Stress is not applied on some system, remember that. It is something, a wrong statement. Stress is never applied on. You apply pressure, you apply force, and as a result stresses are developed inside the system, right? So you can say, if I represent that stress as sigma, so that sigma would also be equals F over A. So you can also represent this work as stress into area into dl. Okay, just to clear that ambiguity, that you don't apply stress, you apply pressure, and as a result those stresses are developed inside the system. Okay, so please use that correct statement. Now similarly, three deltas what? Okay, this is an inexact integral. This is an inexact one. Why inexact one? Because work is not a property. Okay, but this is an exact, because you can find out length at the first state. Length or displacement is kind of a property.
So the first delta defined on that because we are using difference.
Yes, I mean I was just trying to understand, make you understand the concept. Otherwise it should have been dl. Okay, a very small distance. Generally whenever you use these kind of things for your calculus related expressions, you say that it is dl, analytical representation for these displacements. Then there is another thing related to electric power or electric energy. Now if you have, let's say, some battery and you have its terminals, and you are attaching those two terminals with some motor or some electrical appliance. If this is V1 and voltage at this stage is V2, so obviously you would consider this as del V, and if some amount of current is passing through it due to this voltage difference, so this is, I think it should be like this. I'm not good at those electrical subjects, but still I think you can understand it. So how do you define this power, electrical power? Or you can say the rate, I would say this is rate of work done by this system on that electrical appliance which is attached to it. How you can do it? VI, isn't it? That's how you can define it, right? So there are other examples as well. I mean, you can find out if you are trying to put something into a gravitational field or into some magnetic field or electric field, electromagnetic field, what you can see is that field would also be doing some kind of work on that body, right? So you should be able to represent that work. So in your book, in your reference books, you would find out few examples related to work done in different systems by different fields. Let's say if it is an electrical field, how you can represent that work. If it is something like mechanics, extension of a solid bar, how do you represent this work, right? Similarly, if you are doing it through a battery, if you are putting your body into a gravitational field, into a magnetic field, how you can represent all that work, right? So please go back and check that how do you represent work in different systems. And this is kind of a reading assignment for you guys. So please don't tell me that you do not know how to define the work done by an electrical system. Okay, a very good example could be of work done by a shaft. Like for example, you are trying to move something, and if there is a fan, let's say, just look at that fan. Obviously the motor is rotating. At the back side of that fan, some motor is rotating. So you would see some kind of shaft over there, which is linking the motor with the fan blade, fan wing, right? So it means that motor is rotating. So if that motor is rotating, it is also rotating that fan blade. It means that motor is doing some work on that fan blade. So I mean, you should be able to understand, or you should be able to mathematically model that work. I can just tell you that if you are talking about a rotary systems, you deal with torque. Instead of force, you deal with torque, right? And then instead of translational velocity, in the translational systems, you would be dealing with angular velocity, right? So although there is a theoretical foundation as well, but in that case, power would be, or power transmitted would be, or the rate of work done by the motor on the fan blade would be kind of torque multiplied by omega. Okay, that angular velocity. You can go back and see how do you derive it. But my purpose is just to give you few examples about the representation of work done in different systems in their mathematical form. Okay. So a very important thing again, just to tell you, just look at that. I mean, if all of those examples, whether you talk about work done in a magnetic field, work done in a gravitational field, work done by an electric field, or let's say an electrical appliance, or let's say you talk about that example related to extension of a bar, every time you would see that this work, which is not a property, that would be represented by the product of some intensive property multiply by this. This is the product between some intensive property and some extensive property. Like for example, if I ask you, there is a system f dx. What do you say? Which one is the intensive and which one is the extensive one? This force would be an intensive property and this would be an extensive property. Okay. Now you are already very clear about the definitions of those two things, intensive and extensive. But my point is, so whenever you write down work done by any of those systems, whenever you mathematically model that, you would see that somehow or the other that it is a product of some intensive property into differential of some extensive property. Okay. So in any case, like for example, if I say that I have work done by the electrical field, what you can see is it may be something like that was power. I mean this could be power, right? Is it the power, electrical power? Now if I say this is DI, a small amount of current is developed by that voltage difference. So what you would see is that this is kind of an intensive property and this would be an extensive property. Now due to this similarity by the within the work models done by different systems, does not mean what kind of system it is, you can say that this delta V is kind of a generalized force and this delta I is kind of a generalized displacement, although it is not, but just to relate this thing with the basic definition of work, what you can see is that you call that intensive property as the generalized force. Okay, you just perceive it as if it is a generalized force. Similarly, for that extensive property, you say that it is a generalized displacement, although it is not. Okay, but still you see how these systems are, just to link between the actual work done by that system with the actual definition of the work, just f dot ds kind of thing. So this is generalized displacement. and this is generalized force. Similarly, I can give you few other examples as well. Just look at that, tau, and you multiply it with what? Something, right? To find out work done by the motor on the fan blade. So that tau would be what? A generalized force, not in terms of dimensions. I mean, it is not giving you the units of the force, but still you can see that if you associate it with the actual definition of work, this tau can be regarded as a generalized force, and the other term would be regarded as a generalized displacement, right? So just to link between those two things. Okay, any question? I'm not talking about two forces acting on a body. I'm talking about, like, for example, if someone is pushing this thing, now what would you see? That the force felt by this point plus the force felt by this point plus the force felt by this point, would that be giving you the total force? Not at all. Okay. Yes, fine then. Then what's the difference? Now, why are you looking at it from both the forces? I mean, you should be looking at it as a perspective of net force. I would see as if it is a net force. I mean, obviously it would be F1 minus F2, and the body would be feeling some kind of, let's say, some kind of stress into it due to the net force, not as a result of F1 and F2 individually, right? So that's all for today. Inshallah, we would, by the way, there would be no class on Monday, right? I would reschedule that class just because of my commitment in a symposium at NUST. So I think you would give me the schedule for the makeup of this class, Monday's class. Okay, thank you.